Hello everyone. Today I'd like to introduce WheelSense, a smart automation system designed to improve accessibility, convenience, and safety for wheelchair users. This system uses motion tracking and proximity detection to automate home appliances and monitor user activity. Many wheelchair users face challenges in controlling home appliances and monitoring their daily activity. Simple tasks like turning on lights or adjusting a fan can be inconvenient. Our goal is to create a smart environment that makes daily life easier and safer. Our system focuses on five key objectives. First, motion tracking collects and stores wheelchair movement data. Second, proximity-based automation turns appliances on or off when a user enters or leaves a room. Third, safety monitoring sends alerts if no movement is detected for a long time. Fourth, energy efficiency ensures appliances are only used when necessary. Fifth, remote monitoring and control allows users and caregivers to monitor activity and control devices via an app. The primary stakeholders of WheelSense include wheelchair users who gain more independence and elderly individuals who experience improved accessibility and caregivers who can remotely monitor the user's well-being. Secondary stakeholders include medical professionals and home automation developers who can integrate this system into healthcare and smart home solutions. To understand the impact of WheelSense, let's look at a few examples. First, a wheelchair user can track their movement data to monitor activity levels. Second, lights and fans automatically turn on when they enter a room and off when they leave. Third, if there is no movement for a long time, a caregiver gets an alert. Fourth, users can manually control appliances using a smartphone app.
Okay, in this project, the hardware components utilized includes M5 capsule. Initially, we encountered a board reset issue with M5 capsule, leading us to switch to M560. However, the issue has now been resolved. Both M5 capsule and M560 feature Bluetooth and Wi-Fi modules, along with 6-axis IMU, which we use for detecting wheelchair user motion and communication. Next one is the T-SIM cam, an ESP32S3 board equipped with a camera module and communication capabilities, including Wi-Fi and Bluetooth. We use it as a station installed in each room of the house. Next is a Raspberry Pi 400 running Home Assistant OS. It serves as the home automation module. The last one is the Tapo smart devices used for automated control demonstration. The system architecture M560 is attached to the wheelchair's wheel, broadcasting the BLE signal and continuously publishing motion data via MQTT. The T-SIM cam station detects the BLE RSSI signal and notify the Raspberry Pi when the wheelchair is nearby. The Raspberry Pi then sends the commands to smart devices in each room to turn it on or off. The Raspberry Pi also receives motion data from the M560 via MQTT and store data in the local database. Additionally, the Raspberry Pi transmits summarized data to the company's server via HTTP requests for customer behavior tracking. And in case of emergencies such as fall down or accident of the wheelchair user, the Raspberry Pi can send the notification through Telegram. About the software architecture, at the hardware level, we use C and C++ with Arduino framework and Platform I/O to program the T-SIM cam and M560, which send data to the local server, which is Raspberry Pi Home Assistant OS. We use the Node-RED as the home automation platform, InfluxDB as the local time series database, and Grafana for in-house data visualization. On the company server, all services run inside the Docker container. The backend is built with Python using the MongoDB as the database, Fast API for handling the API requests, and in Grok to expose the local server to the Raspberry Pi. And the front end that dashboard is developed with Next.js using Mongoose for database connection, MQTT.js for real-time data reception via MQTT, and Chassis UI for UI design. For the state diagram, first one is the M560. It runs 3 separate tasks using FreeRTOS, which are the BLE broadcasting, sensor data reading, and data transmission. And the state diagram shows that it initializes itself, set up the BLE broadcasting, configures Wi-Fi and MQTT connections, and continuously transmit motion data via MQTT. Next is the TSIM cam. It initializes itself, set up BLE scanning, configures Wi-Fi and MQTT connections, and checks for nearby M560 devices while filtering out false detection before sending data to the Raspberry Pi. And the Raspberry Pi initialize and connect to the Wi-Fi and receive data from 2 sources, which are the M560 that transmit motion data in real time and proximity data detection data from the TSIM cam. Then it decides whether to turn smart devices on or off based on the received signals. And for the sequence diagram, the process starts with the wheelchair user moving inside the house, where the M560 attached to the wheel continuously communicates with TSIM cam stations and Raspberry Pi, which then controls the smart devices and interacts with the company server. The M560 also publishes motion data in real time, which display on the web-based real-time user interface. In case of an emergency, the Raspberry Pi sends the alert notifications to family members or caregivers. And for the data flow process, the M560 on the wheelchair and the TSIM cam stations transmit data via EMQX, which is MQTT broker. This data is processed and displayed on the user interface, also stored in the database. And then Raspberry Pi use this information to alert to control the smart devices and also send alert to caregivers when necessary.
Okay. Can you hear me? Okay, next we're going to talk about the data modeling. For our system, we start with a robust data model. We track devices and user with unique IDs, storing critical information like creation dates, user locations, and contact details. The device logs capture raw data such as speed, distance, and location, while the admin entity ensures secure access for staff like coaches, physical therapists, and caregivers. Additionally, we monitor if a user has fallen, logging timestamp and value to ensure the timely responses. And next, we're going to talk about the benefits of our system. For the benefits of our system, first, we're going to enhance the accessibility by providing the independent appliance to control wheelchair users. And next, the caregivers will be alerted if the wheelchair user is inactive for too long. And next, we also can reduce their energy consumption by turning off the unused appliance. Also, the caregiver can use the remote monitoring to ensure the well-being of wheelchair users. And last but not least, the long-term activity tracking helps in health analysis. This feature creates a safer, more efficient, and supportive environment for users and their caregivers. Next, for future enhancement and AI integration, first, we can use machine learning models like LSTM and random forest to detect movement changes that may indicate their fatigue or health rates. And next, we can combine motion sensor and cameras to detect falls and send emergency alerts in application. Next, the third one, we can revelate reinforcement learning to predict and optimize appliance activity based on their behavior. And next, we can use like voice power assistant. We can say turn off or turn on the lights to providing real-time update to caregiver via chatbots. And last, we can enhancing the Bluetooth-based proximity detection to reduce false activation. And next, for the conclusion, this project is aimed to enhance the quality of life of wheelchair user by integrating motion tracking and proximity-based automation and smart home control. By leveraging AI in the future iteration, the system can provide like predictive analytics, also fall detection and adaptive automation. And for further, we can also improve the safety, accessibility, and energy efficiency. The next part will be the last part. We have also demonstrate our system. The first video that you see is the implementation of when we use the light detecting. We will let our group member Kazu to enter the room, and then when he enter the room, the light will turns on automatically based on the RSSI value. As you can see, when he come near the sensor, the light will turns on. Yeah, and when he off, the lights will turn off automatically. For the next video, the next implementation is the room changing. When Kazu changed the room from the first room that he just come from is the living room, and this room that where he is now is the kitchen. You can see in the web page that we created that we will show that where is the Kazu now. Like it will show that he is the living room, kitchen, or bedroom. Yeah, it can detect where the wheelchair user is in which room in the house. And next video, we just try to collect data about the wheelchair user moving around to see their acceleration and the gyro of y-axis, axis, and z-axis. And next is the Grafana. Sorry, the Grafana, this screen graph. We can see this screen in our house because it's just a local host, it's not deployed in the cloud. So maybe we can use the monitor in our house to monitor this graph, like to see the behavior of wheelchair user. Yeah. And for the next one is the Next.js. This one is deployed in the cloud, so we can monitor everywhere via application by our mobile phone. Yeah, but in Next.js the information is not too deep, like it's not too deep as much as in the Grafana. Okay, next. The following notification. In case that the wheelchair user has fallen from the wheelchair, there will be a notification appear on the application user. Yeah, as you can see, like it says that has fallen in the kitchen. It's also say their location, which room the wheelchair has fallen. Okay, the next one will be the last one. It is our future work. This one we already have a model of HAI, but we also implemented in the camera module, but we not already combined in our system yet. That's why we consider it as our future work. Okay, that's all for our group presentation. Thank you.
Okay. Okay.